Welcome to Coffee Break, the live stream series brought to you by Microchip Technology, where our mission is to educate, entertain, and empower you to innovate in your designs. I'm your host, Dana Curtis, and you are watching Season 13 of Coffee Break. As always, we're here to dive into the fascinating world of embedded control technologies, integrated circuits, and all things smart, connected, and secure, in about the time it takes to enjoy a fresh cup of coffee. For those of you joining us for first time, welcome. Coffee Break is a live broadcast and we encourage audience participation. Before I introduce our special guest, let's take it over to Aliyah Fahout for some housekeeping items. Aliyah, what do you got for us?
Hi everyone, thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn, and we invite you to participate in today's episode by leaving your questions, comments in the chat, or you can email us at livestream@microchip.com after the broadcast. If you're watching us on YouTube today, go ahead and subscribe to our channel so you know when our next episode is. And if you're watching us on LinkedIn, subscribe to the event so you can get all information related to this episode. Back to you, Dana.
Thanks, Aliyah. Today we have two special guests joining us. Amit Goel is a product marketing manager and Adrian Ocampo is an engineering manager at Microchip Technology. Welcome, Amit and Adrian. You guys are here today to talk about space power solutions for traditional and new space. We've got our coffee ready. Let's start with the obvious question. What is the difference, if any, between traditional space and new space?
The traditional space or the new space, the basic difference between the traditional and new space is that the new space basically relates to the low Earth orbit, which is 1,500 kilometers from the surface of the Earth. So this encompasses, all the projects related with internet surveillance, and traditional or deep space is related with the traditional missions, such as missions to Moon, missions to Jupiter, as well as the missions far out, like Voyager.
Okay, great. Probably the most difficult challenge in getting something to space is cost. Even with private companies like SpaceX driving the cost down, we're still looking at thousands of dollars per kilogram. But obviously that's not the only challenge we're talking about, right?
Yes, there is a big difference when we make a DC to DC power converter on Earth, and when we want to take it to the space. The biggest difference, the number of factors that affect it, one of them is radiation. So there are a number of aspects that affect radiation. So one of them is total ionizing dose. So what is mean by that? So it is basically a cumulative damage caused to a semiconductor lattice for a period of time because of the space environment. And this causes degradation of the parameters and eventual circuit failure. It's measured in TID, and it is, the extent to which it's present is higher in a deep space as compared to LEO orbits. The second key aspect is single events. So single events are basically a transient events caused by the particles, heavy ions, that can, destroy the circuit in one go. Like, just like, hockey player going for the goal and it goes inside the net and your circuit is done. So that's how critical it is. Then there are other aspects such as, mission survival. So that deep space or traditional space, you need to have, higher mission space, mission timing because of the number of, experiments done. So if you're going to Jupiter or, Mars, the overall length of the mission is bigger, whereas for LEO space, new space, is relatively lesser, it's shorter, but nonetheless, the durability is important. And then when you look at the overall systems, space power systems, there are different voltage nodes, different power nodes. So you should be able to cater to those different power nodes. And that's where you need scalability. You need a solution that will, fit for all those different challenges of our system. And as we know, when we want to send anything against the gravity in the space, you require lots of resources, engineering resources, monetary resources, and overall, volume of what you send should be lesser. So, every gram, every kilogram that you send costs a lot. So size, weight, and power are critical. Power density is critical. Efficiency is critical. And as we are entering into the era of new space, it is more important to have a faster time to market. That doesn't mean that the deep space or traditional space doesn't need for faster time, but the challenges are far more for new space. And of course, there are lots of regulations related with regard to the EMI, with regard to the temperature, vibration, and those stringent regulations need to be met. And last but not least, cost. As you see, there are lots of private companies coming into this sector, and the overall volume of satellites is relatively higher in new space, and that is calling for the cost optimization. So all these factors, they affect both deep space as well as new space, and challenges of cost are more stringent. Challenges of time to market are more critical in new space. Doesn't mean that they don't exist in deep space, but these are the overall challenges that we face when you want to send anything into outer space.
Great. So with all these challenges, how easy would it be to experience an in-flight failure?
Well, that would be totally catastrophic. That is something that you wouldn't like to have. This is something that you would like to avoid. The first thing that you would like to avoid. So when we talk about Microchip has got 30 plus years of experience in sending this making customized solutions, and we have zero in-flight failure. So when you look at the overall the system that we provide in terms of DC to DC converter, we could easily bifurcate that into the custom solutions and standard solutions. So when you talk about custom solutions, these are tailor-made solutions made for the customer's requirements. There are lots of stringent requirements related with voltage and power and regulations, and those are like bespoke things made to specification. Whereas standard converters are the ones which are comes in a very standard casing. They have standard ratings, and some of those examples, as you can see here, SF50 120 and SF50 28. Those are the standard converters, rad-hard converters, mainly for deep space. And then recently I introduced LE50 28, which is a converter for new space. So the beauty of the standard converter is that you can use those converters to make highly customized design without having to spend a lot of money having custom converter. Again, there are applications where you have lots of complexity where you would need custom converters, but otherwise you can always have standard solutions for Microchip and use them creatively for the space forward.
Great. So let's build on what you said earlier about deep space. What is the difference between the orbits, and how does that change the design process?
I think just to give you an idea, the geo orbit or geostationary orbit is 35,000, around 35,000 kilometers from the surface of the Earth. So that is quite a big distance. And if you compare that to the low Earth orbit, it's around 1,005 kilometers. Now that is substantial. So just to give you an idea, the airplane flies at around 30,000 to 50,000 feet, which is just 15 kilometers. So it is not that low Earth orbit is very near to Earth. It's still 1,500 kilometers, but relatively, the difference is around 22 times. So that there are different challenges. So in deep space, you have issues such as solar particles, issues such as galactic rays, as well as solar plasma, because you are actually in the outside of the Earth's atmosphere, and you are less protected by the Earth's magnetic field. Whereas in LEO, the low Earth orbit, those challenges are lesser. Doesn't mean that they are not there. So the extent of radiation hardening that you need to do for deep space is far stringent than the one that you need to do for low Earth orbit. And also there are differences in the overall volume. So the constellation gets formed by the LEO satellites, and there are number of small satellites. They form the constellation and provide services such as internet surveillance. So in terms of volume, it's if you look at the market, it's a pretty big market, and so there are certain challenges such as time to market as well as cost. They're far stringent than the outer orbits such as geo orbits, and the speed. So generally, the speed of this LEO constellation is almost twice higher as compared to the deep space orbits. So if you look at overall challenges, the challenges remain same. They are difficult. They are more stringent, as you go away from the Earth, which is in case of deep space, and they are lesser, but they are not like completely not there. There are significant challenges, and at the same time, LEO has got its own challenges in the cost efficiency that it needs as well as in time to market.
So with these stringent needs, it would make a lot of sense for flexibility to be critical to mission success?
Yes, indeed. And that's why if you look at our solutions that we provide in our standard portfolio, they are pretty much similar. If you look at their basic characteristics, they are pretty much similar. And this is mainly to make sure that it becomes easy for customers. So our standard non-hybrid isolated DC-to-DC converter you can use for deep space as well as new space. We've got two different categories, and there are certain common features. So what are those common features? So each and every unit is capable of 50 watt, and we give extensive configurability with synchronization and ability to parallel 4 converters to cater to 200 watts. And these converters, comes with output voltage range from 3.3 to 28, meaning that in single converter, we have got 3.3, 5, 12, 15, and 28 volt. Whereas triple converter, we got combination of those, like 3.3 plus or minus 12 or plus or minus 15, or 5 plus or minus 12 or plus or minus 15. And also you can use triple converter as a dual converter. So that's added flexibility. Again, all these sockets, they got high efficiency, and they conform to the stringent standard of EMI and vibration and temperature cycling. These are very small packages, 3-inch by 2-inch, and 1/2 inch is the depth, 120 grams. That makes them really compact, and they're easily integrable with the other offerings that Microchip provides, namely FPGAs and MCUs. And if you take a deeper look at these offerings, our SA50 series is positioned for the deep space. We have got SA50 120 volt series, which has got inbuilt EMI filter, and we have got 28 volt series for which we provide external EMI filter, and this has got, as you can see, higher TID and SE to cater to those challenges of deep space. On the other hand, our LE50 has got relatively lower rating because the application demand those things, and currently we've got 28 volt series, and we've got lots of capability to customize for any voltage that you need, and again positioned for the LEO mission. So we've got like a standard sockets. They look same. One is positioned for deep space, rad hard. Another is rad tolerant and positioned for all the LEO missions. And they provide all the common features such as high reliability, high efficiency. They're easily configurable, cost effective, and they enable faster time to market for customers, which is a key aspect, and that provides tremendous value proposition.
Great. So let's dive into new space a little bit. Let's talk about the LE50 series.
Sure. The LE50 series is a derivative, really, of our SA50 series, whereas the SA50 series is designed for 15+ year missions, deep space. The LE50 is designed for 5 to 10 year missions in low Earth orbits or even middle Earth orbits. The way we achieve that is through adjustment in our component selection for these modules, that will maintain, the radiation level commensurate with the LE orbit or low Earth orbit. That means slightly lower TID and lower SE thresholds. But we do maintain the reliability for that mission time, 5 to 10 years, while improving on the lead time. Just rad hard parts and military grade parts are long lead time by their very nature. But by maintaining this footprint and construction, we're able to easily meet the different missions while staying in the same footprint. The construction that we adhere to is non-hybrid construction. It's more of a printed wiring board construction, which allows for minimal touch labor, which in turn leads to no lot jeopardy, and as I've already mentioned, faster lead time and design flexibility.
So how do we provide customization?
Sure. We often get customer requests for customizing, different output voltages or accommodating different input voltage levels, and we do that for customers on the SA50 and LE50. We'll go in and redesign the board. It's a fairly fast turnaround versus other construction techniques. Sometimes they ask us to integrate the EMI filter or provide some other functionality such as telemetry. I do have such an example here.
Mm-hmm.
This particular example integrates the EMI filter within it, whereas the LE5028 does require an external filter. So those are the type of design changes that we can support for customers.
That's great. All right, so the LE50 sounds a lot like it's just one component in a total system solution. Does that sound correct?
Yes, that is correct. In Microchip, we have ability to give different offerings for rad hard, as well as that is for deep space, as well as the rad tolerant offerings for LEO space. So this is one example of the offerings for LEO using LE50. So as you can see, the satellite bus is 28 volt. It gets that voltage from the array of satellite. And then since we have external EMI filter for LE50, we got SF200 our filter there. And then if you want to have, if your power requirement is less, which is 50 watt, you can use one. If you want to increase that power, you got scalability to go all the way up till 200 watt, because there are different applications. No two satellites or no two applications are same, and there are different power demands. So this is where LE50 really shines. And then, as you can see, there are a number of configurations that you can make with this, with single and triples. And then after this, and the beauty of Microchip offering, that we also give not only LE50, but we also give POL and the loads basically to convert these voltages into the voltage that could be directly fed to FPGAs and MCUs. And so we have got as you can see, the regulators, we got LDOs, and then comes the brain of the system, which is FPGAs and MCUs. So there are different loads such as the monitoring system, electronics, ion thirst propulsion system, and they require different FPGAs and MCUs, and we provide all the solutions. So if you can see, right from getting the voltage, the 28 volt voltage from the solar array to feeding the final load, we provide everything, and that's kind of real succinct value proposition that we offer. So every satellite needs FPGA and MCUs, and every FPGA MCUs need LDOs, and in order to power those, we need to have converter, and we provide the converter and the entire solution. And again, just to let you know that this is just one example. This is just kind of most simplest example for the viewers, and this is related with LE50. but we have got similar power system architecture for SA50 where we provide everything on the plate. So it's like a IKEA shop where you can get everything that you need to make your mission successful.
That's great. So with that, let's get over to Aaliyah to see what kinds of questions we're getting from the interwebs. Aaliyah, what do we got?
All right, so the first question is from Sneha on YouTube. What features of SA50 and LE50 enable easy configurability?
Yeah, so for both of those designs, Amit mentioned earlier that they do have enable commands. They have this parallel configurability. Along with that, we provide an isolated sync input so that you can actually parallel those so that they're in phase when they're switching. We have a remote sense capability for it. Those are the features that are inherent to the design.
Thank you. Let's wrap it up with one more question here. This one is from Alan on LinkedIn. What design support do you offer?
Sure. Often customers have specific, vibration or thermal requirements, or even change in the design, and we can provide those updated, analyses, including worst-case analyses, and as I mentioned earlier, adjusting even our design to meet their, input voltage and output voltage requirements as needed.
All right, well, thank you guys. Thank you for the audience for sending us your questions. Thank you, Amit and Adrian, for answering the questions. For the audience, if you have additional questions or comments, you can email us at livestream@microchip.com after this broadcast. And don't forget to follow us on LinkedIn and subscribe to our YouTube channel. Back to you, Dana.
Thanks, Aaliyah. Well, that was worth the coffee. I want to extend a big thank you to our special guests, Amit and Adrian, for their knowledge and passion that they shared with us today. It's conversations like these that remind us of the endless possibilities empowering your innovation in the world of embedded control and processing. If today's topic has sparked your interest and you'd like to learn more, I encourage you to visit our website at microchip.com, where you'll find a wealth of information and resources that dive deeper into the world of microchip technology. And if you'd like more Coffee Break, head over to microchip.com/coffee break and click on the subscribe button to get updates for all things Coffee Break. You can also see upcoming episodes for Season 13. And of course, be sure to join us next time on Coffee Break as we explore improving security strength with Microchip's Trust Anchor 101 Security IC. That episode will live stream on Wednesday, July 31st. Until then, stay curious, stay creative, stay caffeinated.